Hello everyone, hopefully you're having a great day today. Today we're going to look at some more things that have to do with circles, and this is what is called tangents. Okay, now a tangent line is a line that intersects a circle in exactly one point. Okay, so if you think about points of intersection and how things can happen with a circle, it can either cross or intersect no times, it can intersect twice, or intersect one time, and that's what's called the point of tangency. Okay. Now we also have something called a common tangent. And now this is a line, a ray, or a segment that is tangent to two circles. So what you should notice in these pictures that I have here, you have a circle. The first one has a line here that's intersecting that circle. That's your tangent line. Now in the second drawing, I've got a bunch of different lines, 4 actually, and those are all different lines that intersect each of those circles once. Okay, so this one intersects both, this one intersects both, this one intersects both, and that one intersects both. Each one time, those are known as common tangent lines. Okay, and there's a bunch of different ways your book, or I apologize, your assignment is going to be, one of the things may ask you to draw these tangent lines or a common tangent line for a couple circles, and that's exactly what you're going to do. You're just going to try and draw the line that intersects both circles one time. Now, tangents lead to a few theorems, and this is one of them. It says, in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. And this is a big one. You can use this for quite a few different applications. But basically what it shows is if you draw a radius, okay, which is this black line here, which I'm covering up in green, and then you also have the point of tangency, which is the black line, which is now orange. Okay, so those two lines are perpendicular if and only if that orange line, or the point of tangency, is an actual tangent line. Okay, so that's kind of what this is saying. It's just one of those proofs that you can use quite a different ways, especially once you get a little more advanced, but we're going to look at a couple relatively basic ideas of how this works and hopefully make some sense of it. So it says here, determine if the line, JK is tangent to circle J if JL is a radius. So they're telling you right now that JL is a radius. We want to know, is LK tangent? I'm full of typos today. I'm sorry. I'll try and get this fixed. So if LK is a tangent. All right, so they're asking you to prove essentially that this right here is a right angle. All right, let's think about what we've got. We've got this right triangle, supposedly, if this works. You've got the bottom value of 15, you've got the radius of 8, and then you've got this segment here is 9. Now what this is saying is it's just this small segment there that's 9, so we need to figure out what is this segment from here to here. Well, if you notice, it's just another radius. So that right there is 8, which makes this entire thing 17. Alright, so you've got a right triangle with a side length of 8, of 15, and 17. Now, it is a right triangle if that follows Pythagorean's theorem. So you go 8 squared plus 15 squared equals 17 squared. All right, so it's a squared plus b squared equals c squared. And then you just start working through this. So 8 squared is 64, 15 squared is 225, and 17 squared is 289. All right, so we add these things together, you get 64 plus 225 is 289 equals 289. So basically what that says is that LK, because it works in Pythagorean's theorem, is indeed perpendicular, which means it's a tangent line. So that's how you're going to use that theorem to either prove something is a perpendicular or prove something is in fact tangent. Now the second thing here, it says JK is tangent to circle L. Find the value of x. So we're looking for x in this case, trying to figure out what that might be. We're going to use the same idea. Right now it tells us that JK is tangent, so that is definitely a right angle there. So we want to set up and use Pythagorean's theorem. So if we take a, which we'll call x here, so x squared plus b, which is 12, so 12 squared, equals c squared, our hypotenuse. Now c is the entire length of that. So you've got the small value x, the small value 8. Using the segment addition postulate, you can add those together and get x plus 8 for that entire side and then we square that. All right, and now we solve. So x squared is x squared. 12 squared is 144. X plus 8 squared. Now remember, when you're doing this, you cannot just square both of those. You actually have to FOIL this. So this is x plus 8 times x plus 8. This goes back to earlier in this class where you use FOIL, or this is a perfect square again. So you end up with x squared plus 16x plus 64. All right, and now you work to solve for x. So if I subtract x squared on both sides, my x squareds will cancel out completely. If I subtract 64 from both sides, I end up with, on my right-hand side, those two 64s cancel out. I end up with the 16x on that side. And then when you take 144 minus 64, you end up with 80. All right, and then finally, you take that and divide by 16. And that gives you an x value of 5. And there you go. All right, so the fact that this creates a right triangle brings Pythagorean's theorem into play, and you can solve the problem that way. All right, so on your own, I want you to pause the video, see if you can solve for x in this case to make this a right angle. So pause the video and give that a try. Okay, let's see how you guys did. So a squared plus b squared equals c squared. So x squared plus 12 squared equals 17 squared. All right, so we start solving this. You've got x squared here. You've got 12 squared, which is 144. So plus 144. And then that's going to equal 289 because that's 17 squared. Now solving for x squared, we're going to subtract 144 from both sides. So you got x equals, that's going to be 145. And then we're going to take the square root of both sides from there. And when you take the square root of 145, you end up with an x value of 12.04, and there's your solution. All right, and that is the side length that makes this a tangent line. All right. Hopefully that makes some sense. Let's keep moving. Now we've got another theorem that works with tangent lines. This says if two segments from the same exterior point, remember exterior means outside, so two segments from the same exterior point are tangent to a circle, then they are congruent. So we've got these two lines, AB and BC. They're both tangent to this circle. They both originate at B, so that means that those two lines are tangent, so AB is congruent to BC. So here's how this can get put into play. An architect is paving two roads that are tangent to a lake. What are the lengths of the roads? All right, so we've got this road originating at this spot over here. They both end up being tangent to this circular lake, which means that since they're both tangent, those two things are equal. So we can take 4x minus 500 and set that equal to x plus 250 and solve. Okay, now this is something, as you have been going through these classes, you should have gotten pretty good at solving equations. So we simplify that way. The x's cancel on the right, the 500 cancels on the left. So I've got 3x equals 750, which means that x, once I divide, x is going to be 250, and there's that. Now, what it's actually asking is, what's the length of the road, not what's the value of x. So we take that 250 and we substitute it there, or we substitute it in there. And it makes sense that we should be able to do both because, like we said, they're congruent. So if you take 250 plus 250, you're going to end up with 500. So the length of that road is 500, and there you go. Okay, now, obviously, it doesn't give us units, so we're not sure. But if they did supply the units, we'd have to put those on there as well. All right, hopefully that makes some sense. If you have any questions, let me know. Otherwise, good luck. We'll talk to you soon.